Welcome to Parallel Circuits. I wanted to talk to you about the characteristic of parallel circuits, what that means, and how we can maybe do some analysis of what's going on with our circuits. Simply put, parallel, we can identify, if we're talking about a parallel-only circuit, it's a circuit where one side is all positive and the other side is all negative. And we can imagine what that would be like if I were to take a 9-volt battery and simply put it across a couple of resistors. You can do this, and sometimes we would put LEDs in series with these resistors to tell whether they're operational or not. I've got a video doing some of that if you want to take a look at that. But let's simply talk about parallel circuits, what they are and how we can look at that. First thing I want to talk about when I'm talking about a parallel circuit, or what I call a parallel-only circuit, is that voltage is constant. In other words, voltage is the same everywhere. So whether if you look over here on the right of this pictorial diagram and look at the schematic, you can see I read 9 volts whether I'm reading resistor 1 or resistor 2. So voltage is constant, so the voltage on R1 is equal to the voltage on R2 is equal to the voltage on R3, etc. The other thing we talk about is that the total branch current is equal to the sum of the branch currents. So if we were going to talk about this, is that, let's say this is the negative side of our battery. The current leaves the negative side, it goes through R1, but it also divides right here. If you can see my little bitty circle here, is it divides here. Part of the current goes to this resistor, part of the current goes to this resistor, then it comes back together. Sometimes we call these points nodes, and wherever we get to the node, or the branch where it branches off, we'll see current divide. So when we're specifically talking about a parallel circuit, we're talking about circuits that divide, or current divided circuits. So this is a current dividing circuit. It splits up the current, if you will. So what goes into a branch, what leaves a branch comes back into a branch. So we simply state that as total current is equal to the sum of the branch currents. We add up individual branch currents. We also need to understand, in point 3 here, is that branch current is independent of any other branch. So regardless of what's happening with resistor 1 or resistor 2, if we were to add a resistor 3 or resistor 4, it would not affect the branch current. This resistor is going to get the current it needs, this resistor is going to get the current it needs. So as I add or take away branches, it will add and take away current. The next thing is that you need to understand that as I add resistors in this circuit, if I add resistors in parallel, is that my total resistance is going to be smaller than the smallest resistor. So if you've ever dealt with stereo equipment and you start adding resistors in parallel, what you're doing is you're decreasing the resistance, you're increasing the current, you're increasing the power. So at some point you'll exceed the power rating of those speakers and probably end up blowing a fuse or throwing a circuit breaker or something of that type. So we need to understand that as we are adding branches or adding additional components, is that we are increasing current, we are increasing power, and that the design of that circuit does have some current and power requirements, and once we exceed that, it's going to go into safety features, just throwing a breaker or blowing a fuse. And the last thing I want to talk about is that the total power is the sum of all the power consumed. So as we are adding branches, we're adding current, we're increasing power, so all that affects our circuit overall. And so what I want us to think about, what happens when additional resistors are added. So when another resistor is added to the circuit, so we go from 2 resistors to 3 in this scenario, we see that total resistance will decrease, which means that our total current will increase, the total power will increase, and voltage is still going to be the same. So if I had this 9-volt battery here and I add and I take away resistors, it does not affect the total voltage or the source voltage in this case. So let's take a look at what we actually do when we're calculating resistors. If I were to have 2 resistors in parallel, I can look and do what we call a product over the sum formula, where the total resistance is equal to R1 times R2 divided by R1 times R2. We'll look at an example in just a moment. And then if I add a third resistor, we can use the reciprocal formula. And the reciprocal formula will work with 2 resistors also. I'm just indicating that there's a product over the sum, so you don't have to deal with the reciprocals. So in this case, it's the reciprocal formula is written there. It's the 1 over the 1 over formula. And you could take a look at how we would do this. So we say that R1 is equal to 1K, R2 is 2.2K, R3 is 3.3K, R4 is 10K. So there's a couple of scenarios showing you how you can calculate those formulas out. And I've got the notes available for you in Moodle. If you're one of my Moodle students, you can take a look at that. And so this shows the how this would work if you have 2 resistors, 3 resistors, and then 4 resistors. And as I indicated, you see that as I add resistors, total resistance goes down. And that may seem counterintuitive. It seems like resistance would go up, but you have to understand the configuration of the circuit is to add resistors in parallel. So just think about if I'm driving down the freeway and I open up an additional lane of traffic, then the traffic is going to flow easier, the resistance is less. And it's the same way with a circuit. As I add additional branches, it's easier for current to flow, and so that would indicate that resistance is less. And then I show here a resistor that if you were to do a Verpi chart on this, we would have 3 resistors in parallel. There's a diagram here of what that would look like with a battery, schematic here. There is the reciprocal formula showing you how I calculated resistance. And then since we know that voltage is constant, we know it's 9 volts everywhere, and I know what my individual resistors are and what my total resistance is, I can calculate the amps and the watts, or the current and the power, and I filled that out in my Verpi chart. So see if you can duplicate my answers. And then in troubleshooting, there's a couple of issues that we can look at in troubleshooting. One is I can have a shorted circuit. So if any of these resistors are shorted, that would mean that my entire circuit is shorted. I would have 0 ohms, which would short out the power supply. So the fuse on the power supply would blow. So that would indicate that you have a shorted circuit. So we don't want to do that, but we do want to talk about that. At the very bottom note here, it says when any resistor shorts out, the entire circuit is shorted. So that's easy, it's dangerous, and it's unfortunate. So, but if anything's shorted out, the whole thing is shorted out. So let's talk about opens. Remember, we indicated in one of our notes here at the top is that the branch current is independent of any other branch. So if one of these resistors opens up in this scenario on page 4, if one of those resistors opens up, that means that if the resistor goes away, so does its current. So I've indicated that the issue would be if my current normally should read 39.13 milliamps. So if my current is less than that, then one of my resistors is open. And I've gone and looked at the branch currents at 6 milliamps, essentially 11, 9 milliamps, and 13.13 milliamps. So if I look at these currents, if that current goes away, that means that resistor is open. So that would look like when the total current is 33.13 milliamps, that means R1's open. When current's 28 milliamps, that means R2 is open. When current is 30 milliamps, that means that R3 is open. And when the current essentially is 26 milliamps, that means R4 is open. So just wanted you to think about those 2 scenarios, when there's a short or when there's one of these individual resistors is open. So that resistance goes away, current goes away, and then you would look at your total current and compare it to normal reading and find out which of the branches is open. I hope this helps out, and I'll see you next time.